Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is electrically controlled systems. Our objective today is to take an introductory look at electrically controlled systems and discuss the advantages, applications, and characteristics of such systems. The Big Bad Tech channel is about power. When I use the term power, I am speaking of not only the time rate expenditure or production of energy, and the metaphorical extension of a person skilled in the contents contained in the playlists as having the ability to control and influence their own professional path, but also the ability to control a system, be it a factory, a wind turbine, or a robot to do what you tell it to do when you want it done. Most often, electrical energy is converted to another form at the point of use. A motor converts electrical energy into rotational mechanical motion. This motor could be used to move a heavy load or propel a car at a speed and distance an unaided human would be incapable of achieving. A battery charger converts electrical energy into chemical energy. This stored chemical energy can be withdrawn from the battery as electricity in a remote location. Electrically driven pumps can pressurize fluid, and this pressurized fluid can be used to lift a massive object and keep it lifted until such time it becomes necessary to lower it safely to the ground. Electric heaters can heat water for domestic and industrial use, and electricity can keep the interior of homes and factories comfortable and well lit in all seasons. Industrial applications of electricity are used to assist workers with physical labor and free them from monotonous, physically demanding, or dangerous work. This being said, motors, pumps, hydraulic cylinders, heaters, turbines, and other machines are not thinking machines. They are as self-aware as a hammer, a screwdriver, or a sharpened piece of flint. It is for this reason electricity in its direct form is used to perform sensory and logical functions for automated industrial control processes, communication, and information technology. Data is sent, received, processed, and stored using electrical signals. Switches and sensors form the eyes and ears of automated industrial processes, and hardwired relay-based ladder logic, or the programmed instruction sets written inside ruggedized computers called PLCs or programmable logic controllers, make decisions based on these incoming signals and issue outputs to devices like solenoid-actuated directional control valves or contactors. Automated industrial control systems increase output, quality, efficiency, and safety in addition to providing repeated precision and greater accuracy. It is this aspect of electricity in its direct form that is used to control, as the name implies, an electrically controlled system. At its most basic level, electrically controlled systems are commonly used to start and stop the movement of actuators. An actuator is a device that takes one form of energy and converts it into mechanical movement. Actuators can be differentiated by the form of input energy and the form of mechanical movement they produce. Input could be electrical, hydraulic, pneumatic, thermal, chemical, etc. And the mechanical output could be linear, rotational, or oscillation, which is a form of partial rotation. An electric motor is an example of an actuator that converts electrical input into rotational mechanical output. A solenoid is an example of an actuator that converts electrical input into linear mechanical output. A hydraulic cylinder is an example of an actuator that converts hydraulic input into linear mechanical output. Pneumatic cylinders are an example of linear pneumatic actuators, and so on. Keep in mind that additional mechanical linkages can modify this initiating motion and translate it to more usable forms. For example, a rotating electrical motor can drive a conveyor belt in a straight line, and a hydraulic cylinder with a pivoting trunnion or clevis mount can tip or tilt an attached load. Numerous examples of actuators exist, and despite their differences of input energy or form of mechanical movement, they can all be electrically controlled. A magnetic contactor can start or stop a motor, and a solenoid-operated directional control valve can stop or start a hydraulic cylinder. In addition to starting and stopping actuators, electrically controlled systems can change direction and modify operating characteristics of actuators. such as varying the rotational speed and torque of an electric motor, and varying the extension or retraction force or speed of a hydraulic cylinder. Advanced electrically controlled systems can also perform timing, counting, sequencing, comparison, computational, data processing, and communication functions, and more. On a very basic level, switches and sensors can be viewed as the inputs to an electrically controlled system. These are the eyes and ears of an electrically controlled system. If the eyes are blind or disconnected from the brain or pointed in the wrong direction, then the brain won't react to it. Actuators like motors and hydraulic cylinders are the primary outputs of an electrically controlled system. They are in effect the hands and feet of a system, being that portion that does the actual lifting, lowering, moving, punching, pushing, or pulling. The actuators, however, only move at the request of the electrically controlled system. A contactor starts or stops a motor. A solenoid-operated valve extends or retracts a hydraulic cylinder. If the motor is disconnected from the contactor, or the system doesn't close the contactor, the motor won't start. If the cylinder doesn't have fluid supply, or the solenoid-operated valve doesn't shift, the cylinder won't extend or retract. Hardwired connections, or programmed instructions internal to the electrically controlled system, are the brains of an electrically controlled system. The brain makes the decision to start, stop, or change the direction of an actuator. If the brain receives wrong input, it will act appropriately on falsified data. If the brain is wired incorrectly, it will act in an unintended manner. If the outputs are disconnected, the brain will issue orders, but none of the actuators will obey. With this brief diversion, I've already prepared you to troubleshoot an electrically controlled system. Where is the problem? The input, the output, or the brain? At its most fundamental level, troubleshooting an electrically controlled system is the determination in which realm the problem exists. That's ultimately what troubleshooting is. It's the successive bracketing down and down into a smaller and smaller target area until the problem is found and rectified. Good troubleshooters do this in an efficient and systematic method, and most importantly, get it right the first time. Don't look for your lost puppy in the mountains if you lost him at the city park. He's most likely befriended a charming street person or a teenage runaway that expects a stiff reward for his return. We'll return to discuss troubleshooting an electrically controlled system in greater detail before we close up shop. One of the most fundamental characteristics of an electrically controlled system is the differentiation between the control signals and what is being controlled. The control signals are typically low voltage, low current, low power signals and are entirely separate and electrically isolated from that aspect being controlled, whether it is hydraulic, pneumatic, or high voltage, high current, high power electricity. The control signal is often called a pilot signal. The power input is often called primary input, and you'll hear me use these terms interchangeably. The pilot is not the primary. The primary is not the pilot. The pilot is in charge of the primary, and the primary only acts at the request of the pilot. It is for this reason I typically initiate discussions about electrically controlled systems using an electrically controlled hydraulic system as an initial example. Even those with no requisite knowledge of hydraulics can differentiate between the dual aspects of this system. It is readily evident that the hydraulic system is the power or primary portion of the system, being that portion of the system that does the actual lifting, pushing, pulling, or punching, and it is being controlled by a low voltage control or pilot signal that merely tells the hydraulic components when to shift valve positions. There is a clear distinction not only between the pilot and primary function, but also pilot and primary form. Hydraulic components conduct hydraulic power, but only do so at the request of the electrical pilot signal. Consider this simple single-acting cylinder and a solenoid-operated two-position, three-way directional control valve. In its de-energized state, the spring offset ensures that the directional control valve is dumping to tank, and the cylinder is retracted by the spring. The solenoid-operated valve simply moves the valve into a new position when the solenoid is energized. When a low-voltage electrical control signal is sent to the solenoid, the valve shifts to the straight-through position, and pressurized flow enters the cap end of the cylinder, and the cylinder extends. It is very obvious and very clear that the low-voltage control or pilot signal told the solenoid-operated directional control valve to move to a new position and conduct primary hydraulic power to the actuator. How different is this application from an electrically controlled motor? Consider an industrial motor that requires 480 volts three-phase AC to operate, however, does so only at the request of a programmable logic controller, a PLC, basically a form of ruggedized computer that operates at 24 volts DC. The principal point of interaction between the control or pilot and the power or primary signals for this type of system is a contactor. A contactor is akin to a solenoid-operated directional control valve in an electrically controlled hydraulic system. In its de-energized state, the contactor is in its open condition. When the coil of the contactor is energized by the low-voltage pilot signal, the contactor closes the electrically isolated primary electrical power switches. There is a very clear distinction between the different flavors and magnitudes of pilot and primary electricity, despite their superficially similar labels. It is very obvious and very clear that the low-voltage control or pilot signal told the magnetic contactor to move to a new position and conduct primary electrical power to the actuator. Let's ignore the overloads in series with the primary contacts for now. We'll discuss overloads when we discuss motor starters and circuit protection devices. As self-evident and clear the distinction and separation of pilot and primary is in an electrically controlled hydraulic system, so too must be the distinction and separation of pilot and primary in an electrically controlled motor system. The pilot signal is low voltage, low current, low power electricity, entirely separate and electrically isolated from the high voltage, high current, high power primary input, and must always remain so. The only interaction between the pilot and primary electrical signal is via magnetic or mechanical means. They are electrically isolated for a reason, and the primary reason is safety. Pilot signals for modern electrically controlled systems are ordinarily 120 volts AC, 24 volts AC, or 24 volts DC as representative examples, with a notable progressive movement favoring 24 volts DC. It is plainly evident that these levels of electricity are not nearly as dangerous as high voltage electricity used to deliver power to an industrial motor, or nearly as dirty as oil-based pilot signals for a hydraulic system. That's the point. The customary use of low voltage, low current, low power electrical pilot signals offer a degree of ease, safety, and isolation for operators and technicians assigned to install, maintain, troubleshoot, upgrade, and repair electrically controlled systems. Again, the control or pilot signal is low voltage, low current, low power electricity, entirely separate and electrically isolated from the power or primary signal. The primary or power input to a system could be high voltage, high current, high power electricity, or hydraulic or pneumatic power. The primary signal is governed by the pilot and only acts at its request. The separation of the pilot and primary aspects of an electrically controlled system offer a degree of ease, safety, and isolation. This is another reason why I like introducing electrically controlled systems using an electrically controlled hydraulic system operated by DC control voltages. It allows individuals with the most basic of electric skill sets to launch into an early discussion of electrical controls. DC electricity and a basic understanding of hydraulics are very low hurdles that need to be cleared, and the same concepts employed on these systems can then be extrapolated into those systems employing three-phase AC primary and single-phase AC pilot signals. If you're already skilled in AC circuit analysis, you'll simply have a better appreciation of the peculiarities. However, it's not absolutely necessary to understand every single last detail for the purposes of this general level discussion. An electrically controlled hydraulic system operating on DC voltage needs to be supplied with not only hydraulic power, it must also be supplied by a power supply or battery capable of providing the requisite DC control voltage. There is a clear and definite distinction between not only pilot and primary function, but also pilot and primary form. For AC systems incorporating motors, the level of control voltage necessary to operate an electrically controlled system ordinarily comes from a control transformer. This device steps down high voltage primary input to a safe and more usable pilot value. In the case of an electrically controlled system employing three-phase AC, can actually use the line-to-line voltage between two of the phases as the input to the primary coil. Let's say an electrically controlled system using 480 volt three-phase AC as primary input requires 120 volts single-phase AC as a pilot signal. The primary input to the control transformer would be the 480 volt single-phase AC between any two of the three phases, and a 4-to-1 step-down transformer would step this down to 120 volt single-phase AC. If this system was controlled by a 24 volt AC pilot signal, this control transformer would have to step this 480 volt AC input down 20-to-1. The secondary winding output of the control transformer could be grounded or ungrounded. The location of the grounding point and the reasoning behind this I'll explain later when we go into greater detail about ladder logic. The control transformer is ordinarily protected by fuses either on the primary side, the secondary side, or both. If this system was to be controlled by a 24 volt DC pilot signal, not only would this primary input have to be stepped down a similar amount, it would also have to be rectified or changed into DC using a traditional power supply. Given the dual nature of the pilot and primary aspects of an electrically controlled system, they are often represented differently in schematics. Again, let's start with our electrically controlled hydraulic system as an initial example. It is self-evident that there must be two schematics for this system. One being the primary hydraulic schematic, the other being the electrical pilot schematic. In this simple example, there exists a single interaction point between the two aspects of the system, that being solenoid A on directional control valve 1. When push button 1 is closed in the electrical schematic, DCV1 solenoid A is energized. On the hydraulic schematic, the energized solenoid A would shift DCV1 to the straight-through position and the cylinder would extend. Solenoids are typically represented as something similar to a resistor in the electrical control schematic and a box with a diagonal slash through it on the primary hydraulic schematic. The label DCV1 Sol A clearly designates that this is the same device and the principal interaction point between the pilot and primary aspects of this electrically controlled hydraulic system. Similarly, a means of differentiating between the pilot and primary aspects of an electrically controlled system incorporating motors must be used. Again, there must necessarily be two schematics for this system, one being the primary electrical schematic, the other being the electrical pilot schematic. If the pilot and primary schematic are to be illustrated on the same sheet, ordinarily the pilot is drawn in thin lines and the primary in thick lines, although this sometimes isn't the case. In this simple example, there exists a single interaction point between the two aspects of the system, that being the coil on the M contactor. In the electrical pilot schematic, when push button 1 is closed, the M coil would be energized. On the primary schematic, the energized M coil would switch the normally open contacts to their opposite or closed state, and the motor would start. Coils are typically represented as a circle in the control schematic. The label inside the coil, M clearly designates that this coil controls contactor M in the primary schematic and serves as the principal interaction point between the pilot and primary aspects of this electrically controlled motor system. There are obvious differences between them, but if you want to think of it this way, coil magnetically linked with a contactor is analogous to a solenoid-operated directional control valve. Both primary devices, the contactor and the directional control valve, are the devices that actually conduct power. However, they do so only when they're pilot devices, the coil in the case of the contactor and the solenoid in the case of the solenoid-operated valve tell them to do so with a low voltage control signal. The contactor and the solenoid-operated valve are basically performing the same function, the establishment or interruption of primary power at the behest of a control signal. One could use traditional schematics to draw the control portion of an electrically controlled system. However, in practice, this becomes very cumbersome for a complicated circuit, so the control schematic is ordinarily drawn using something called a ladder logic diagram. The low voltage output of the power supply or the control transformer is represented as the left and right side of vertical upright rails of a ladder, and the conductive path from left to right is represented as a rung on that ladder. In the case of our electrically controlled hydraulic system, when push button 1 is closed, it completes a path from the high left side through the solenoid to the low right side. A ladder logic diagram basically flattens out a series path into a single line, and it makes readily apparent that in order to complete a conductive path from the hot or high side through solenoid A to the low or neutral side, one must close push button 1. A ladder logic diagram for the electrically controlled motor system is almost identical. Again, the ladder logic diagram flattens out the series path of the traditional schematic into a single line, and it makes readily apparent that in order to complete a conductive path from the hot or high left side through the coil M to the low or neutral side X2, one must close push button 1. Ideally, the power supply and the control transformer establish electrical isolation between the primary and pilot voltages. If one needed to ground the reference output of a control transformer, one customarily does so on the X2 side. This ensures that overcurrent protection devices like fuses and circuit breakers function as intended and ensures that an errant connection to ground does not inadvertently start a hydraulic system or motor. This implies that ladder logic diagrams always use high-side switching arrangements and that input devices like switches are placed between the high side and the electrical load, be it a coil or solenoid, and the low side or grounded upright rail. Switches on the left, loads on the right. The one exception to this rule are the normally closed overload contacts associated with a motor starter, which we'll discuss later. Again, ladder logic is a means of flattening out a traditional electrical schematic into a readable line. The high side is the left-hand vertical upright. The right side is the low side or neutral vertical upright. A switch, switches, or other input devices on the left selectively connect or disconnect an electrical load on the right via conductive rung on the ladder. Inputs on the left, electrical loads on the right. This ensures that overcurrent protection devices like fuses and circuit breakers function as intended and ensures that an errant connection to ground does not inadvertently start an actuator. The one exception to this rule are the normally closed contacts associated with a motor starter, which we'll discuss later. The electrical loads in a control schematic represent either the coils of contactors or the solenoids of solenoid-operated valves used to start or stop primary power in the primary schematics. These principal interaction points must appear in both schematics. As our ladder logic diagrams increase in complexity, you'll learn that there is to be one electrical load per rung. Electrically controlled systems can be divided into two general categories: those that employ traditional hardwired relay-based ladder logic and those that use a programmable logic controller, or PLC, a form of ruggedized industrial computer to execute the logical functions necessary to stop, start, change direction, modify operating characteristics, or perform timing, counting, sequencing, comparison, arithmetic, data processing, communication functions, and more. Hybrids of these systems exist. However, as the PLC is becoming progressively cheaper and more powerful, there is a notable movement favoring these devices. Additionally, small devices, sometimes called programmable logic relays or intelligent relays, combine a number of basic PLC common functions into an inexpensive small package for small systems that can almost be considered an intermediary between these two extremes. Regardless, the logic internal to an electrically controlled system using either traditional hardwired relay-based ladder logic or a programmable logic controller is essentially the same. The components that comprise most electrically controlled systems can be divided between devices that deliver inputs to the system, the devices that get issued outputs by the system, and the devices or program instructions internal to the system. Additionally, high-level electrically controlled systems may also include devices that communicate and store or retrieve data. For this introductory discussion, let's stick to the basics: output, input, and internal connections. We've already spent some time discussing two basic output devices: the coil of a contactor and the solenoid of a solenoid-operated directional control valve. A contactor turns on or off an electrical motor at the request of a low-voltage control signal. A solenoid-operated directional control valve shifts a fluid power valve when told to do so by a low-voltage control signal. These type of output devices form the principal point of interaction between the pilot and primary aspects of an electrically controlled system, and their function is to tell the primary device when to establish or interrupt service. Other output devices exist, such as pilot lights, displays, alarms, or buzzers, which can be considered forms of indicators that simply tell human operators what condition the system is in. Indicators typically only interact with the control level voltage. However, this isn't always the case. Outputs can again be thought of as the hands and feet of an electrically controlled system, those parts that perform physical labor or announce status to the outside world. On the input side of an electrically controlled system, these devices can again be thought of as the eyes and ears of a system that acquire data about the outside world. Input devices ordinarily take the form of switches or sensors. Switches are different than sensors, and the primary distinction is that of digital versus analog nature of the two. Switches are discrete and clear in nature and can be in one of two mutually exclusive positions, either closed or open, and never a little bit of both or halfway in between. An operator turns a system on or off. A pressure switch tells the system pressure is above or below a certain set point. A sensor, in contrast to a switch, measures some quantity and produces an electrical output proportional to the magnitude of the quantity being measured. Switches could be considered sensors. However, I'm using the term sensor to suggest a sensor not only detects the presence or absence of a condition, it also measures and quantifies it. Sensors are a type of transducer, which converts physical movement, temperature, pressure, or other measurable quantity into an electrical signal. A pressure sensor, for example, measures pressure inside an enclosed vessel and outputs an analog voltage or current value that can perhaps be later digitized with appropriate resolution for later processing or storage. Sensory input can also be used by an electrically controlled system to make decisions about when to activate an output and with how much force or speed. The continuously changing nature of an analog signal output of a sensor implies that an electrically controlled system making use of high-resolution data is slightly more complicated than one employing simple on and off digital signals of switches, but when you get right down to it, they're both inputs to an electrically controlled system that makes decisions about the state of respective inputs and issues appropriate outputs. Returning to our discussion of switches, switches can be further subdivided into two different categories: manual and mechanical or automatic switches. Manual switches, as the name implies, require a mano or hand or foot or elbow or other human body part to hit them. Manual switches are points of human-machine interaction and could be a push button, a selector switch, a toggle switch, or a drum or cam switch. Manual switches are meant for human interaction. A mechanical or automatic switch is a two-state switch that does not require human intervention to change states. An example would be a limit switch, a pressure switch, a float switch, a temperature switch, a magnetic proximity switch, or a rotational speed switch. Mechanical or automatic switches, as the name implies, allow an electrically controlled system to function without human intervention. An example might be a pressure switch that starts a pump when pressure falls below some desired value and stops it when pressure rises above a certain value. The differential between the cut-in and drop-out pressure is known as span, or hysteresis, or override, and is necessary for the proper operation of such a system. The differential prevents the pump from bouncing back and forth between on and off when operating in a region close to the set point. We'll take a closer look at different types of manual and mechanical or automatic switches and some sensors in later lectures. Devices or programmed instructions internal to an electrically controlled system are those components that do the actual comparison of inputs and issue outputs. This is where electrically controlled systems employing traditional hardwired relay-based ladder logic and those employing PLCs radically divide. Both types of systems require input in the form of switches or sensors, and both types of systems issue outputs to contactors or solenoid-operated valves or indicators like pilot lamps. However, those systems employing traditional hardwired relay-based ladder logic really are composed of physical devices, called relays, really physically connected to one another in a specific manner, whereas those employing PLCs use user-defined instruction sets that mimic the function of relays. One can already see an advantage of the PLC in contrast to traditional hardwire relay-based ladder logic. To change the functionality of an electrically controlled system employing traditional hardwire relay-based ladder logic, one must physically rewire the system, whereas to change the functionality of an electrically controlled system employing a PLC, one must simply reprogram the system. This is to suggest that electrically controlled systems employing PLCs are significantly easier to install, modify, and troubleshoot than those employing traditional hardwire relay-based ladder logic. This is a major advantage for all industries that require repeatable and dependable functionality from an electrically controlled system. This does come at a price in terms of both monetary and time investment. PLCs have been traditionally considered more expensive and come with a significant learning curve in comparison to traditional hardwire relay-based ladder logic. However, that is changing as PLCs have become cheaper and easier to use. Regardless, the instructions written inside a PLC program are programmed in the exact same manner as one would employ a relay inside an electrically controlled system employing traditional hardwire relay-based ladder logic. The fundamental difference between these two types of systems can kind of be summated as this. The control relays inside an electrically controlled system employing traditional hardwire relay-based ladder logic are real. The instruction set inside an electrically controlled system employing a PLC mimics the function of control relays. A control relay is a device internal to the logic of an electrically controlled system and only switches control level signals. A switch associated with a control relay could turn on or off a coil or a solenoid, which in turn would drive a primary load. Control relays are seldom used to directly drive a load and would only be found doing so in the lowest of low-power applications. Control relays, as the name implies, switch only control level signals. A control relay can take many forms. General-purpose control relays have a collection of normally open and normally closed switches that change states when the coil of the relay is energized. Timer relays perform timing functions, and counter relays can count. The control relays mimicked by a PLC instruction set perform additional high-level tasks. Whether the control relay is a physical device or a mimicked instruction set, it can be thought of as a device with a coil and a set of associated contacts that change states when the coil is energized. Both the coil and the contacts of a control relay switch only control level signals. It is the arrangement of input devices, output devices, and internal control relays that dictate the function of an electrically controlled system. Our previous examples employed a single input device, a switch, and a single output device, a contactor or a solenoid-operated valve. Consider the following modifications of these electrically controlled systems, and with it the different functionality these modifications bring. Consider the simple addition of two switches to our ladder logic diagram consisting of push button 1 and push button 2 in series. This is the logical AND operator. The only way an operator can energize the solenoid of DCV1 Sol A is if both push button 1 and push button 2 are simultaneously closed. This is a common safety feature for a device that requires an operator to have both hands cleared from the workspace prior to extending a hydraulic cylinder. An example might be a hydraulically driven press or a shear. Alternatively, consider two switches, push button 1 and push button 2, wired in parallel with each other. This is the logical OR operator. The solenoid would energize if push button 1 only was closed, if push button 2 only was closed, or if they were both simultaneously closed. This is a common feature for a device that requires an operator to energize the solenoid of DCV1 Sol A from two different locations. An example might be a hydraulically driven lift with two independent control points. These two control systems both make use of two inputs, the two push buttons, and one output, the solenoid. There are no relays internal to the ladder logic, so one might be led to believe that there is nothing internal to the ladder logic. However, the two systems function in radically different manners. For our first system, both push button 1 and push button 2 must be simultaneously pressed for the cylinder to extend. For our second circuit, either push button 1 or push button 2 can be pressed for the cylinder to extend. The ladder logic itself, being the electrical relationship and the physical wiring of the two switches, is the internal construction of the electrically controlled system and dictates its behavior. Consider the maintenance, repair, upgrade, and modification of hardwired electrically controlled systems. If the first system needed to be modified such that it had the functionality of the second system, it would necessitate the physical rewiring of push button 1 and push button 2. If this was one of many such systems, imagine the sheer volume of tedious labor it would necessitate unscrewing, removing, rerouting, and reattaching all those wires. This is the major advantage of a PLC. As alluded to previously, the PLC is a ruggedized industrial computer that evaluates inputs and issues outputs based on a programmable instruction set. If this electrically controlled system's behavior was governed by a PLC, it would still require two inputs, push button 1 and push button 2, and it would still issue one output to the solenoid. However, the programmable instruction set requires no physical rewiring, but rather a simple reprogramming if the functionality needs to be changed. This is a major advantage. Consider additional functionality to this electrically controlled system offered by slightly increased complexity internal to the ladder logic diagram. These extra rungs act almost like parallel paths if one was to draw this circuit using traditional schematics. Consider a control relay CR1 and its associated contacts, normally open CR1A and normally open CR1B. In its de-energized state, these associated contacts would not allow conduction from the high to low side of the ladder logic, and both solenoid A and the M coil of the contactor would be de-energized. If, however, an operator were to simultaneously press both push button 1 and push button 2, the coil of CR1 would be energized. When the coil of CR1 is energized, its associated contacts change states. Normally open CR1A closes, as does normally open CR1B. The now closed CR1A contact energizes DCV1 Sol A. The energized solenoid A shifts DCV1 to the straight-through position, and the cylinder extends. Simultaneously, the now closed CR1B contact energizes coil M. Coil M closes the M contactor, and the motor starts turning. The hardwired relay logic, or programmed instructions internal to the ladder logic, now offer the ability to coordinate what was once two separate systems. This could be used to create a hydraulically extended, electrically rotated drill. We'll learn in later lectures how relays and programmed instructions internal to ladder logic offer the ability to latch, unlatch, i.e. remember and clear previous states, sequence, interlock, count, compare, coordinate, communicate in time operations. Again, inputs in series internal to the ladder logic perform the logical AND function. The only way the electrical load on the right of the rung can be energized is if all contacts in series are closed. The electrical load would be de-energized if any contact in series is open. Inputs in parallel internal to the ladder logic perform the logical OR function. The electrical load on the right of the rung can be energized if any contact in parallel is closed. The only way the electrical load can be de-energized is if all contacts in parallel are open. The hardwired connections or programmed instructions internal to the ladder logic can perform numerous other functions, including but not limited to latching, unlatching, interlocking, sequencing, counting, comparing, coordinating, communicating, and timing operations. Let's return to close out our earlier discussion about troubleshooting an electrically controlled system. Consider this electrically controlled, hydraulically extended, electrically rotated drill system. What could go wrong with this system? How could it break? How could you identify potential problems? The most important step in troubleshooting a malfunctioning system is to first understand how the system is intended to operate. That's what we just did. We looked at the hydraulic primary, the electrical primary, and the ladder logic diagram controlling both primary aspects of the system. I will be so bold to say you simply cannot perform troubleshooting without performing this step. Yes, there are tricks of the trade and shortcuts to be employed, but without a solid understanding of how a system is intended to operate, any troubleshooting attempts without this base knowledge is superstitious ritual and button pushing unbecoming of a technician. Only when you understand how something is intended to work can you pinpoint where a problem may lie. At its most basic level, troubleshooting an electrically controlled system is the determination in which realm the problem exists. Is it electrical? If electrical in nature, is it in the electrical pilot or the electrical primary system? Or is it hydraulic? Or, more sinisterly, is it an electrical problem that appears to be hydraulic in nature, or vice versa? That's ultimately what troubleshooting is. It's the successive bracketing down and down into smaller and smaller target areas until the problem is found and rectified. Good troubleshooters do this in an efficient and systematic method, and most importantly, get it right the first time. Keep in mind there is no limit to the wrong that can happen in the real world, but let's imagine some scenarios and see if you can assign them to one realm or the other. Let's say an operator notices a rapidly expanding pool of hydraulic fluid collecting below the system. This is quite obviously hydraulic in nature. A hose or connection may have developed a leak, and in a high-pressure hydraulic system, that pinpoint leak could become a dangerous jet of high-pressure fluid. The system needs to be immediately powered down, and the leak needs to be detected. The pool ordinarily collects below the leak, and if not directly below the leak, the path of the leaking fluid should be easily recognizable with a visual inspection. Let's say upon responding to a troubleshooting scenario, you notice an ozone or burned electronic smell upon entering the building. This is electrical in nature. Burned electronics have their own characteristic smell, and you can rest assured that your nose will lead you to this solution. One might notice damaged wires, or one might notice a damaged coil or contact. Let's say the cylinder extends and retracts, but extends very weakly. My first indication that this is hydraulic in nature, since the control aspect of the system is allowing the cylinder to extend and retract. If the cylinder is extending, but extending weakly, my first point of inspection would be the pressure relief valve setting. If the pressure relief valve is set too low or damaged, the cylinder will extend, however will extend weakly. Let's say the cylinder does extend and retract, but does so erratically and noisily. Again, the problem is not electrical in nature, since the control system is allowing the cylinder to extend. My first point of inspection would be the reservoir fluid level. If entrained air is caught in this system, pseudocavitation is occurring, and our actuator would extend erratically and noisily. Additionally, I would check the viscosity and temperature of the fluid to ensure that it is compatible with our system. Let's say the cylinder extends but will not retract. My first point of inspection will be the spring on the single acting cylinder, or perhaps a jammed piston in the cylinder. Additionally, consider the case where the drill is caught. This system does not have a clamping cylinder, and any workpiece being drilled through might shift in position and jam the piston in the cylinder. We'll discuss later electrically controlled systems that not only incorporate clamp cylinders, but also verify that the workpiece is being clamped. Let's say an operator cannot get the cylinder to extend and the drill will not start. The problem is very clearly inside our control system, since both the cylinder and the drill motor actuate at the behest of the control system. If neither the cylinder extends nor the drill starts, my first point of inspection will be the common control system. If, however, the cylinder did not extend, yet the drill started to rotate, I would inspect the second rung of our ladder logic control system, or I would check our hydraulic power unit. Solenoid-operated valves typically have a pilot light associated with the solenoid, which allow an operator or technician to verify if the solenoid is being energized. Additionally, the valve being a physical device that shifts position, one should be able to hear or feel movement. The relays themselves are again physical devices. One should be able to see the coil being energized, and when the coil is energized, those associated contacts should change to their opposite states. Pressure, flow, voltage, and current ratings at various points within our system should be able to identify the source of our problems. Another great technique for practicing troubleshooting scenarios is to mentally insert an error into our system. If you really understand this system, you should be able to predict how the system will react. Consider a broken wire in the second rung of our ladder logic diagram. If both push button 1 and push button 2 are simultaneously closed, control relay CR1 would energize and the associated contacts would change state. However, the broken wire in the second rung of the ladder logic diagram would not allow DCV1 solenoid A to energize, yet the third rung would allow the drill motor to rotate. In this case, the drill would rotate, but the cylinder would not extend. Consider loss of the L2 phase in the three-phase power supply. If push button 1 and push button 2 were simultaneously closed, the cylinder would extend, yet with a loss of one of the phases inside of a three-phase AC power system, the three-phase AC motor would have difficulty starting. Before we close out troubleshooting, consider the intended function of this system. An electrically controlled system does what it has been designed to do, and if you design a machine to destroy itself or drill a hole through your hand, it will do so without a moment of hesitation. Electrically controlled systems are again not self-thinking machines and merely act out the instruction set inside the programmable logic written by the user or hardwired into the relay-based ladder logic. Consider an operator simply so tired of keeping both hands on push button 1 and push button 2 while the cylinder extends, and so desperately longing to take a smoke break. The operator takes it upon themselves to attach a low resistance wire in parallel to push button 2, effectively making push button 1 the sole input in charge of extending this cylinder. As if that wasn't enough, the operator takes another jumper wire and bypasses the normally open contact CR1B, effectively keeping the drill constantly spinning. This operator, by modifying the hardwire connections, has effectively modified the behavior of the system with potentially disastrous consequences. It's only a matter of time before this injudiciously modified system damages itself, valuable raw materials, or mangles the operator it was intended to protect. This is to again suggest that machines do not think, but only act. You can always trick a machine by jumping a switch or forcing a desired output, but it may not be the wisest or safest course of action to do so. Alright, that's about it for this brief introductory discussion on electrically controlled systems. A housekeeping note before we close up shop. This introductory lecture on electrically controlled systems is meant to service both the hydraulics and electrical control of hydraulic systems playlist, as well as the complete electrical control playlist. If your interest is exclusively in electrically controlled hydraulic systems, realize you'll be leapfrogging a tar pit of pertinent electrical background and dealing exclusively with the hydraulic aspects of electrically controlled systems. One might think the electrical and hydraulic aspects of a system are totally independent of each other, but one needn't look further than the pump central to the operation of most hydraulic systems to find an example of a hydraulic system that requires knowledge of motors and contactors. This brief step into the tar pit having been complete, let's fully immerse ourselves and begin thrashing. How are we going to protect the motor-driven pump from sustained overload conditions? The answer is with an overload device. What's an overload device and how does it work? The answer is it's part of a motor starter, being the means of starting and stopping a motor and protecting it from sustained overload conditions. We are now hopelessly mired in the tar pit, and any further thrashing will only serve us to get further entangled. It is for this reason that the hydraulics and electrical control of hydraulic systems playlist largely separates the electrical and hydraulic aspects of systems, and most examples use 24-volt DC control voltages. Do not for a moment assume that this is always the case. There are solenoid-operated valves and control relays that run on 24 volts AC and 120 volts AC, among other magnitudes and flavors, and sometimes electrically controlled hydraulic systems need to start a motor-driven pump. The only reason I'm purposely dividing the subject material in this manner is that the prerequisites of basic DC electronics and basic hydraulics are very low hurdles to clear. These hurdles having been cleared, one can gain an early exposure to electrically controlled systems. As one further develops electronic skills to include single-phase AC circuit analysis and three-phase AC circuit analysis, those base skills can be brought into the larger picture as we progress into the full electronically controlled systems playlist. It really is all connected, but one can't make connections by thrashing around blindly in the tar pits. If you follow the path I've laid out for you, you'll progressively make more and more connections with more and more material. If you stay in your lane, you should feel comfortable with those targets inside your lane. If you want to look outside your lane, that's okay too. The first part of the electrically controlled systems playlist is this lecture, which serves as the briefest of brief introductions to the topic. The next several lectures introduce key cast members of the electrically controlled systems family, principally the solenoid-operated valve, the principal interaction point between the electrical pilot and primary hydraulic aspects of an electrically controlled hydraulic system, the contactor, the principal interaction point between the pilot and primary electrical aspects of an electrical controlled system using motors, the overload, a means of protecting a motor from sustained overload conditions, the motor starter, being a combination of a contactor and overload, serving as a means of simultaneously starting and stopping a motor and protecting it from sustained overload conditions. The control relay, the principal logical element internal to an electrically controlled system. Additionally, we'll review basic circuit protection devices like fuses and circuit breakers, and take a closer look at some typical manual and mechanical or automatic switches used as inputs to an electrically controlled system. If you've got time to do so, I'd recommend maybe revisiting the circuit protection and switches lecture from way back in the Basic Electronics 1 DC Circuit Analysis playlist prior to moving on to these lectures. It may help to refresh the hardware-specific aspects and functionality of these devices as applied to basic circuits and review common terminology before moving on to the specifics of these lectures. Once we get a good look at these devices, we'll move right into incorporating these devices into increasingly complicated electrically controlled system applications that can start, stop, change direction, modify operating characteristics, time, count, sequence, compare, communicate, and more using ladder logic. Systems of unimaginable complexity can be constructed using switches, sensors, programs, and outputs. Closed-loop control of actuator position, force, and speed can be achieved with amazing precision and accuracy at speeds surpassing human perception. I must remind you, though, machines do what they have been told to do. If inputs report false data, if the internal logic is somehow flawed, or if the outputs somehow malfunction, the system won't work as intended, and those unintended results could have grievous consequences for the industrial process the machine controls and those individuals that rely upon the proper functionality of this machine. In conclusion, this lecture took an introductory look at electrically controlled systems. We identified the primary purposes of electrically controlled system, differentiated between the controller pilot and the power or primary inputs, and differentiated between switches and sensors. Additionally, we briefly introduced the contactor, the principal interaction point between the pilot and primary aspects of an electrically controlled system incorporating motors, the solenoid-operated directional control valve, the principal interaction point between the pilot and primary aspects of an electrically controlled system incorporating fluid power devices, and control relays, the principal logical element of an electrically controlled system. Additionally, we introduced programmable logic controller, which is largely replacing hardwired relay-based ladder logic, but interestingly enough, is still programmed using symbols and techniques largely identical to relay-based ladder logic. The principal difference between these two different methodologies being that hardwire relay-based ladder logic must be physically rewired to change the functionality, whereas PLC-based systems can be simply reprogrammed to change the functionality of the system. We discussed the logical AND operator, the logical OR operator, and had a brief discussion about troubleshooting electrically controlled systems. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.